extension of the stuff that I had you guys do on Friday. So Friday, you did a couple examples for me. I think there was 3 questions to finish it off. Yesterday, you were supposed to do 4. I want to show you what some of mine looked like for those questions. Compare what you did with what I demonstrate. And then if you've got any questions about if you did yours differently, don't assume you did yours wrong. Just if you did it differently or if you got a different value, I'll take up anything that you want to know about any of this stuff. So this is the graph paper I provided. There's space at the top for a title, so you absolutely have to have a title. This one's reaction distance versus velocity. This is the graph for 1A. Reaction distance is on the side. I put velocity on the bottom because reaction distance depends on how fast you're going. You may have gotten a different slope than I did. You do not have to get the same slope because you were drawing a line of best fit. This is the line of best fit I chose to draw. I got a slope of 0.75, which gives me the equation reaction distance is equal to 0.75 times your velocity. And my line actually ended up going through the origin. My scale was that every 2 big squares here was up by 5. That's how I chose to do that. Are there any questions about how I did number 1, or if you did number 1 different, you want to give any questions about it? Okay, there's no questions. Did we do it? It looks cool. What kind of slope values did you guys get for your line of best fit? Yeah, Lena. You got 2/3. Okay. Alexis, what'd you get? You also got 0.75? Okay. Vine, what'd you get for a slope value?
I had multiple. There was 3/5, 3/4, 3/4, and
How many lines did you draw?
only one, but the different points had different values. I was doing it wrong. I wasn't going to call it, so I don't quite understand.
That would you watch the video?
No.
Oh, that would
I'm not on
that would
Teams
make
yet.
it difficult. You're not on what?
I'm not on Teams yet.
You should be on my Teams. Wait, you just didn't sign into Teams?
No, I haven't.
Okay, that's different. Okay. So I also do see your page there. I do want you as much as possible. You're going to think, I'm wasting paper. That's fine. As much as possible, throw 1 question per slab of graph paper.
This is one question. I just did multiple tries.
Well, no, if you did multiple tries, you should have done on multiple graph papers. Like, I want, like, the outside edge should be your axes. Like, don't cram things, don't make things small. One of the first things one of my first year physics teacher said to us in U of V, if ever you're graphing or you're drawing a diagram for something, you draw it, you erase it, you make it bigger. You draw it, you throw it away, and you do it again bigger. Like, use the space. The trees are already dead. Put their corpses to use. Use the graph paper. So this is what my number 1 looked like. Did anyone get different slopes? Syra, what'd you get for a slope?
I did that one wrong.
Okay. You're pretty sure you did it wrong?
Yeah.
Okay, I'll take your word for it. Iyad? Okay, those of you who say you did it wrong, there's a few of you now who said you did it wrong. What did you do? What do you mean you did it wrong?
My points were like not in like a corner thing, like in the middle.
What do you mean?
Like the slope I got was 7/6.5.
I see. Oh, did you... 7/6.5. 7/6.5. Come on. You may have just inverted it. Like, you may have just done, like, swap the y and x axis. Like, what did you graph velocity up the side?
Yeah, but I didn't use the whole thing.
Okay, so yeah, not using the whole page is gonna make it a little bit Yeah, it's going to make your slope harder because you're not going to have as many spaces. And because if I invert my slope, that's 1.3, and 7 over 6.5 is 1.1. So that tells me also that you just flip the y and x. Yeah, did you do the same thing? You flip the y and x? Interesting. What do you mean? Yeah, let me take a look. Yeah, no, I want to see it. Yeah. And I want to take the time, because we're doing a lot of graphing this semester. I want to take the time to make sure we're cool with this stuff now. Okay. Your predicted time was 6.5 seconds. So you have equals. Well then, what was the, this? Did you have your? That's a decent line of best fit. Okay. You said your math said it should have been 80, but your thing said 6 and 7, 6.5. Interesting. I'll take a look at it again. So that's what the first one could have looked like. That was 1A. Here's my graph for 1C. This one's kind of gross, because if you do graph 1C, and you do try and connect the dots, I mean, it doesn't look linear. Like, it's going to be hard to draw a line of best fit through a graph like this one, because you got points there, 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 there. So if you, this straight line here is my straight line of best fit. But it also, I did grab one of the French curves that I'm going to show you guys how to use today. And you can actually throw a bit of a curve through this one. You didn't need to analyze this one, you just needed to graph it and describe the differences between the two graphs. There was no analyzing for an equation here. So it should have looked a little odd to you perhaps. The line of best fit was certainly not as clean as the other one. So that was what I did for 1C. My graph for number 2 looks like this. This was distance versus time for that cart. Distance went up the side, because distance, how far you travel depends on how long you've been traveling for. So I put the time on the bottom. And for this one, I got a slope of 0.3. What did you guys get for your slopes for your lines of best fit? Did you only get kind of a round 0.3? What'd you get, Leanna? You got exactly 0.3? Wow, look at that. Compare what you got with what I got. And this wasn't just a round to 0.3. Like if we use the rules for sig figs, there's a 2 sig figs in this one, so this thing needed to be rounded to 2 sig figs. So that 7 is going to make that 9 a 10, which makes that a 3 and a 0. But yeah, using sig fig rules, I round that to 0.3. Which gives me this equation, distance equals 0.3 time plus b. So this is the one that you guys said was a little bit weird. So let's take a look at what mine did. What was your slope for that one, Yad? 0.3 over 1.2, so 0.25. Okay, so if I look at my, because I want to compare mine. You said at the 2 meter mark, 6.7, which is what I would have gotten. I want to check my equation now. solving this thing for the time, 2 meters divided by 0.3. I don't know, man, if you use the equation, it's pretty bang on, even with yours. Like if you want, if distance equals your slope, 0.25 times time, to solve this thing for time, I put my distance in there, the 2 meters in there, and I divide it by 0.25. Oh yeah, you did get 8. Okay, I could see that being interesting. I got 0.3, you got 0.25. Interesting. So that tells me some variation in your line of best fit. Interesting. I'm not totally convinced you did anything wrong. It's just, so when you draw your line of best, like it'll take practice to draw your line of best fit. I would have to take a look at what you did for your line of best fit again. The reason I drew the one that I drew, like mine, I tried to split the difference as much as I could. Like I've got one here that's, one up at the top that's basically on the line. I had this point that was basically on the line, almost on the line. This point that was like the same distance over the line as this one was. And I tried to split the difference between these two. Like the only difference with what you did versus what I did is I have more practice drawing lines of best fit than you guys do. This might have been your second one. And so to get a feel for it, it just can take time. Like if you handed yours in and I'm using mine as the key, I don't think there'd be anything I would mark wrong. You didn't do anything wrong. You just drew a different line of best fit. And doing these things, which is why today I'm hoping you guys brought computers, because I asked Mrs. Reed to tell you yesterday to bring computers. If not, we'll go grab them from the lab. Today I'm going to show you guys how to use Google Sheets and or Excel to plot this and to do the line of best fit for you. To take your guess out of it, the computer will do it using a statistical analysis of the points that you give it, which makes it a whole lot more robust and accurate than what you might feel you were doing by hand. So we're going to do that today, but we're going to do that in a sec. So that was number 2 here. You're fine. Letter F was, what would the distance traveled be in 18 seconds? I just plugged into my equation, would be 5.4, because that's way beyond where my scale goes over here. I ended up at 7 seconds. To put into 18, you have to put in the equation. So that's 2. Question 3. Question 3, I wanted her to, and I'm assuming she did, tell you not to connect these dots because I want to show you guys how the French curve works. So here's what we're aiming for. Here's mine, all nice and actually curved together. I'm hoping you guys through yours on the graph. Okay, fantastic. That's actually good because I'm seeing a whole bunch of us do this. Which is nice, but at least we're all on the same page. If you haven't done 3, grab a graph out for 3. Let's do it together. I will redo 3 with you. Okay, so here's my graph paper, and I need the data for 3. Where are those values? Okay, so intensity and in lumens and distance in meters, the intensity of a lamp emitted, or the intensity of a light emitted from a lamp is recorded at the various distances away. So the way this works is that intensity, for lack of a better word, intense, that light will change depending on how far you are away. So intensity is dependent on distance. So I'm going to throw distance down here. My distance in meters is going to go on my x-axis down here. And I'm going to put intensity over here. Intensity in lumens. I don't know why I did the curvy L, but I did. And then my scale, my distance scale goes up to 50. So I'm just going to call every 5, 10. Effectively what I'm doing is going up by 2s. 2, 4, 6, 8, 10. 10, 20. Every major square I'm going to call 10 more. 30, 40, 50 is going to look like that. And then I have to go up to 100 lumens. So if I go up 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, same scale. Let's go up by tens again. Every major square is 10. So 30, 40, 50, 60, 70, 80, 90. Am I recording? Sweet, I am. And then 100 is going to be right up here at the top. So then the data says that at 10 meters, the intensity is 100 lumens, so that's going to be one of our data points right there. At 20 meters, it's 25, so that's a substantial drop. So 25 is halfway between 20 and 30. So 20 meters, I'm going to put it right in the middle there. And then at 30 meters, we're all the way down at 11.1. 30 meters, we're at 11.1. So if that's 10, that's 12. Halfway is going to be 11. And then 40 is 6.3, so that's 2, 4, 6, and just a smidgen above 6. And then 50 and 4 are bang on. So that's what that graph should, the points should look like. And I'm really hoping that it's obvious to you that this line is curved and should be curved. If it's not obvious to you, well then you and I can sit and have a conversation about what you see versus what I see. But it's curved graphs like this that we use, curved, not rulers, but curved edges. This is called a French curve. I think I might actually have enough here. 1, 2, 3, 4, 5, 6. I have 10. So we're going to have to do some sharing. You two get to share. The 3 of you get to, no, you 2 get to share. And you have to be Diego and Rafa. Just here, you get your own because you're sitting so far out in isolation. Looks like it's just the front that's sharing. There you go. So, and there's more. There are more of these curves. I'll show you the other 2 that I have. Every curved edge on these French curves, all of them are French curves, every single one of these lines represents a different possible mathematical relationship between these points. Some of them are going to be logarithmic, they might be parabolic, they might be cubic, they might be exponential. Every single one of these curves represents a different mathematical function. To cover all of the different possible relationships between these different phenomena. So, let's take a look at what this looks like, and here's how you use it. You want to throw your French curve on the graph, and you're just going to kind of move it around until it mimics. See, like this, it wouldn't work. I've got these ones down here aren't lining up, even though I'm right on top of this point up here. So you kind of have to get the hang of, again, it's just like with a line of best fit. You kind of got to play with it until you're like, yeah, I think this curve kind of lines up. So I'm going to take this, and if I get to like, as I curl around, I'm using these 3 points down here at the bottom, the 20 point, the 30 point, and the 40 point, to kind of like just to be my floor effectively as I curl this French curve around. And then once I'm happy with what the thing looks like, assuming we ever get happy with what the thing looks like, let's do that. None of them are going to be perfect. Because the French curves aren't necessarily big enough to cover everything. But I get a curve that goes through these 3 points, and then I'm just going to, this is the cardinal sin of graphing, freehand this, or even I can try pulling it around. Can I try pulling it around? I can use the other side of this thing to kind of pull this around. I'll do it that way. I'm not going to freehand. I'm going to use the other part of my French curve, I'm going to flip the French curve over. I'll say this, so the computer's in the way. And get it to draw me the bottom half, not bottom half, but bottom chunk of that graph. So I just flipped it around and I got the same kind of idea. And so I get a graph that looks like this. This is obviously not linear, but it allows us to still make predictions. What would we predict the intensity of light at 25 meters to be? Well, 25 meters, we can just go up here. 25 meters is right there. And now we can actually make this prediction because we've got a curve. 25 up to the curve and over. So that is going to be 25, and that's going to be 10, 12, 14, 16, and a bit. It's not quite halfway, so it's not quite going to be 17. I don't know, 16.5? Maybe. It's above 16. It's not quite halfway. I wouldn't call it 17. And then what would be the distance where the light intensity is 50 lumens? You'd go the other way. You'd go up to 50. Grab a different color. An intensity of 50 is right here. Over to the line. And then straight down. It's going to be in here somewhere. So that intensity is going to be, again, it's not quite halfway. So I wouldn't call it 13, maybe 12 and a half. And if you're curious as to what the actual relationship is, oh, come on, why computer? Smarten up. Why are you going so slow? It looks like it's oh, here we go. Illumination intensity on a surface is inversely proportional to the square of its distance. So this graph is 1 over root. So the intensity I is equal to 1 over the square root of the distance from the light source. Oh, sorry, I lied. Nope, it's not square root, it's squared. 1 over d squared. That makes more sense. Intensity is equal to 1 over d squared. So this is what a 1 over d squared graph would look like. And so we can actually test this and see how good our French curve is. We wanted, for question C, what would we predict the intensity of light to be at 25 meters? So using this equation, the intensity at 25 meters should be I equals 1 over 25 squared. So 1 over 25 squared. Wow, that's really small. What am I doing wrong here? Well, it is 16. Well, it's 0.0016. Okay. Am I doing this wrong? Is inversely proportional to the square of its distance. Inversely proportional is that. Okay, so then maybe it's doing something different. But this would give us 0.0016. So clearly there's something going on here that I'm missing. But there is a close enough relationship here that it gets getting a little fishy. So there it is. That's how the French curve works. Question 4, which I would have wanted you to try. I did want you to try and do. Did anyone get 4 done? We didn't do 4. Okay, let's do it together. Let's take a look at 4. So 4 there's a few things going on with 4. Bless you. 4 says to choose an appropriate scale and plot the graph of those points with t values on the y-axis and sketch the shape. So it wanted you to graph the relationship between t in seconds, or the period of a pendulum, and L, the length of the pendulum. So if we're going to graph those two, and it says here we want the period on the y-axis because the period depends on the length. So for something like this, I would probably actually turn my paper on its side, because we're doing period up this way and we're doing length over this way. And the length is going to go up to 100. So I'm going to do the same thing I did before. I'm going to call this bottom length. This is length on my x-axis now, and I'm going to go up by tens like we did before. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. You don't have to always go landscape. You can turn the thing into portrait mode as well. Huh, interesting. And then we need the period to go. The longest period is 1.93 seconds and the shortest period is 0.8. So if we went up to 2, 1, 2, 3, 4, 5, 6, 7, 8, there's 8 of these things. If I call that 2, and I go up 1, 2, 3, 4, and I call that 1, then this one's going to be 0.25, 0.5, 0.75, 1.25, 1.5, 1.75, and then each one of those squares is going to be 0.05, I think. Yeah. One of these squares represents 0.05, just to cover as much of this graph as I can. That is how I would scale this thing. Sorry, like that. And now putting these points on here, at 100 centimeters, we're at 1.93. So if that's 1.75, that's going to be 1.8, 1.9, 1.95. So that right there is going to be 1.93. Did I do that right? 1.885. Oh no, it's going to be higher. It's going to be here. Well, if that's 1.75, that's going to be 1.8. That's going to be 1.85. That'll be 1.9. So halfway up there, and now it's going to be way over here at 100. So I'm going to graph that first point is going to be right there. Now my next point is 81, which is halfway between 80 and 82 down here, and 1.77, which is going to be halfway between 1.75 and 1.8. So that point is going to be right there, kind of in the middle of space. Right in the middle of that square. 1.58 and 64. 64 is right on that line there. And 1.58 is going to be, well, that's 1.5, so that's 1.55, and that's 1.6. So again, it's going to be 1.5, 1.55, 1.6. So it's going to be halfway there. 1.42 and 49, so 49 is going to be halfway between 48 and 50. And then 1.42 is going to be, that's 1.25, 1.3, 1.35, 1.4. So 1.42 is halfway up there. And I needed 49. So we're right in the middle of that square. Now we need 0.96 and 25. So 25 is going to be there, and 0.96 is going to be up here. So that's going to be 0.95. So 0.96 is going to be just above that line. And 25 is going to be halfway between 24 and 26. So that's going to be like right there. And now all of a sudden it should become clear that this is not, like, these looked like they could be straight, but there's no way this line is going to be straight, including that piece down there. It's going to start to curve in. And so the last one we're going to have is 16 and 0.8. 0.8 is right there, and 16 is right there. So that's that point there. So we can see that this is starting to curve down. So if I grab my French curve, and now it's going to be the other way this time, I'm going to see what I can do with this. The staples do kind of make it a little bit difficult. This one's weird. Did I screw up this piece? This one was 49 and it's too high. It's one too high. 25, 30, 35, 40. It's barely too high, but it is too high. But again, that is also the data that was recorded, so maybe maybe the data recorder screwed up. Maybe it's not us. Yeah, because if I want a curve of best fit, honestly, a curve of best fit is probably going to look like this. Oh, that's my thumb. Don't do that. Or we're going to get a curve that looks something like that. That could be a curve of best fit. It doesn't hit that one. It doesn't hit that one. It goes between those two, splits the difference there, splits the difference here and here. But that's a reasonable curve for what this thing could look like. And then there is a technique that actually exists called linearizing. And it depends on, like, when you're linearizing something, it depends on what this base relationship is. And you're going to have to we make guesses all the time in math, and your computer's actually going to show us how to do that today. But if you take a look here, the question does tell you, now that you've graphed period and length, let's go ahead and calculate the square root of all these lengths and graph those. So we're going to graph, instead of having period and length, we're going to graph period and root length. So here's what that's going to look like. I'm going to graph it on this one. So I'm still going to, I did that wrong. You know what, I don't want that one. I want this, nope, I don't want that one either. I got points there. I want a clean piece of graph paper. Where's my clean piece of graph paper? Here's a clean piece of graph paper. We're graphing, and it's the same way. You know what, I will set it up. I'll set it up the same. I'll put period over here because the period hasn't changed. I'm still going to go up to 2. 1, 2, 3, 4. I'm still going to go up by the same scale on my period axis. But now down here, instead of length, we have root length. And I'm still going to go up to, well, now I'm going to go up to 10. So I could use the whole thing, or I could just go, no, I don't want to do that. 1, yeah, let's go by ones. Why not? 1, 2, 3, 4, 5, 6, 7, 8, 9, and that last one there is going to be 10. So I'm still using all of my graph paper. And now when I throw these points on here, the first one's going to be 1.93 and 10. So 1.93, again, these ones are all still up by 0.05. So this is 1.25, if that helps. 1.5, 1.75. So 9.3 is going to be halfway between 1.9 and 1.95. And 10 is going to be right on the line. Or if something looks like that. My next one is 1.77 and 9. So 1.77 is just above 1.75. That point there. 1.58 is going to be, and 8. It's going to be there. 1.58 and 8. 1.42 and 7. 1.42, so that's going to be 1.3, 1.35, 1.4. it's going to be 1.4 and 7, so 1.42 and 7 should be slightly up. 0.96 and 5, 0.97, now we're below. So it's going to be 0.75, so 0.96 and 5 be right there. Because that's the 0.95 line. And we're going to have 0.8 and 4. 0.8 is that guy there, 4 is that guy there. And it should be at least a little clearer to us that we've actually succeeded in linearizing this thing. If I throw a ruler up, I could totally reasonably draw a straight line of best fit through all that data. It's harder to do with a ruler you can't see through, but I'm going to do it. If you need to grab a ruler, they're on the front. I'm going to draw a line of best fit through these points. Maybe something looks like this. I could have made it a little steeper. Maybe I don't want that line of best fit. Maybe I'm going to do this line of best fit. Let's grab a green one. Could have made it a little steeper. Thanks, Lena. Now let's get more like that. Maybe my line of best fit could look like that. Or maybe it's the same line of best fit, but I slide it up a little bit. Oh, okay, let's go that way. Let's draw another one. So I've got 3 lines on there that I could reasonably all call different lines of best fit. Each one's going to give me a different slope. I think that actually... So we calculated the square root of L for each data on the length on another sheet of graph paper. We plotted this. This is what this graph looks like. I did the calculation. What is the equation for the graph? Y equals mx plus b. If we take a look at what we've got here, if I'm going to use y equals mx plus b, my y value is period. My x value is the square root of length. If I extend these lines of best fit to the y-axis, we're going to get different y-intercepts. That's that one. There's that one. Actually, that should be straighter. So that one actually kind of goes through 0. This line of best fit is going to be negative. So we can do a slope calculation for any of these two. I just need points that actually go through the grid. I want to use the blue line. I actually think it's my best line of best fit. There's a point that goes through the grid line right there. And then there's going to be a point that goes through the grid line I can go up there. So that's where I'm going here. Sorry, that's messy. My computer's in the way. That guy there. So that's the slope calculation I'm going to use. Your line of best fit might look different, and that's fine. I want you all to do this calculation now. I want you to tell me what slopes you get for whatever line of best fit you drew. Like I said, I drew 3 of them. I'm picking my blue one. So my slope there is going to be, it's going to rise how far? That line is at 0.65, and it goes up to 0.95. So that is a rise of 0.3. No, that's a 1.95. That's a rise of 1.3. You can't see what I'm writing because I froze the screen. Because I want you to do it on your own volume. And then this is going to go from 3.4 2 sig figs, it's going to be that. Okay, what kind of slopes you guys got? Here, did you do it? Did you do it? What's your slope? What did you get for your slope of your line of best fit? Okay, calculate me a slope. Does anyone have a value? Yeah, Lena, what'd you get? 1.9 is rounded to 1. It rounds to 1.9. Okay. Anyone else get a different slope? Yeah, did you get a value? It rounds to 0.19. So you and Lena got the same slope. Sweet. Brian, you need a calculator, don't you? Here you go. You've had 2 weekends to get a calculator, man. You can't take 20 minutes to go to Staples and get a calculator? You don't live close to anything. There's not a single Staples, Costco, or a Walmart within 20 minutes of your home. Go to Costco. Just curious, did you get a slope? Sorry? You're doing it now? Okay. To 0.8 or 0.18? Take a look at your numbers again. What was your rise and run? Your rise was 7? You have to use your scale when you're looking at rise and run. You can't just count squares. Yeah, you actually have to use your scale. Every square goes, if your graph the same as mine, every square goes up 0.05 and every square goes over 0.2. Okay, so we got 2 people with basically the same slope. Asira, what'd you get? Let me see. Can't just count squares. Yeah, we got to actually make sure we use the scales that the graphs are in. Right? Okay. My scale I chose, each one of these squares are worth 0.2 horizontally and 0.05 vertically. So sorry, what number do you now? 4.9. Sweet. It rounds to 1.9 or does it round up to 0.2? Okay. And I got 0.2. Mine was 0.1 and then the 9/6 repeats. So if I'm rounding that thing to the correct number of sig figs, there's 2 sig figs here, there's 2 sig figs here. Rounding my final answer to the least number of sig figs when I divide, it gives me a value of 0.2. So if you got a slope of 0.19, I got a slope of 0.2. For lines of best fit that we drew independently, that's really good. Last semester I got 0.1875, which would round to 0.19 to 2 sig figs. So that's great. those of you who got in and around there. So that would make my equation that the period then is going to be equal to 0.2 times the square root of the length plus, and now my y-intercept on this blue line, which is the one that I used, happens to be 0, which is sweet. Last semester, I wasn't quite so lucky. Last semester, my equation was a little different, but that's what I got now. Period is equal to 0.2 times the square root of the length. And so then the last part of this says, according to your equation, what would be the period of a pendulum that was 70 centimeters long? So even though we've got root length as part of our equation, we can just we can plug this in, go for it. This is 4F. So then the period is going to equal 0.2 times the square root of, and this thing is in, yeah, everything's in centimeters. Sweet. On a 70 centimeter long pendulum. Oh yeah, I took my calculator. That's why I found my calculator. So 0.2 times the square root of 70. I got 1.67 seconds. It's actually 1.673, but 1.67. And now just for funsies, let's go back and get off of the root graph and go back and take a look at what it would have been on the curved graph that we drew. If I can find my curved graph, it was right here. So if I want 70 centimeters is going to be right here. Out of here. 70 centimeters is right here. So I could take my 70 centimeters, I could go up to the graph. That's right there. And this line is that's 1.55, 1.6, it's just over 1.65, which is right on the money. So we could, using the linear graph and coming up with an equation, or just reading it off of our curved graph, getting the same value, which is great. So one of them, we had a line, we linearized it, found the equation, plugged it into the equation, or again, we read it right off the curved graph. There's a lot going on here that's, I think, really quite cool. Questions about this? Questions, comments, concerns? Some of you did it, some of you didn't. Are we feeling like, are we a little bit more comfortable with some of this stuff? Because we got a lot more practice ahead of us of the same stuff. Like it's not like a math class where I'm like, oh, so you're not comfortable, now let's look at a new topic. Now we're going to do more graphing. So what I want you to do is I want you to flip to this. I want you, if you have your computer, get it out. I know there's only 25 minutes left, but we're gonna get through as much of this as we can. Grab your computer out. If you need a computer, come with me. We're going to go to the Super Lab. I'm going to grab one, and I'm going to walk you through how to use Sheets and Excel for this. You need a computer, come down. got Windows on your machine, I'm going to start with Excel, but if it's a Chrome OS, then you've only got access to Sheets. If you've got something crazy like a MacBook, I don't know, what do you have on there? Do you have access to Excel on there, or is it whatever Apple's version is? It works with Office? Okay. But do you have it on there? You got it on there? Okay. I'm going to get rid of this. Yes, I'm going to add it back in. So this will be on the video too. Aha! Love it. Okay, so I'm going to start with Excel, which you need to see on the screen. Please work. Haha, love it. Excel. Okay, so I've done what I can. Have your instructions out beside you. I'm going to be referring to them, even though I'm going to be showing you stuff on the screen. So we've got we need to make a table. So I'm going to create a blank workbook. I'm going to make it, stop doing that. I'm going to make a table, and I'm actually going to do question number 4, just as to show you what this is going to look like. So I'm going to have period, or big T in seconds, and I'm going to go L in centimeters. I'm going to fill this thing in. So I got 1.93, 1.77, I had 1.58, 1.42, 0.96, and 0.8. 1, 2, 3, 4, 5, 6 values. Yeah, I got 6 values there. And if I think I've got this backwards. I need to go like this. I'm sorry, guys. We're going to go like this. Like that. I'm going to kill that. I'm going to go there. Because if I'm not mistaken, it requires that you go X, then Y. So that we want this to be on the Y-axis, so I'm putting it on the right. And now we're going to go this way. I've got, oh yeah, right. I had 100. I had 81, I had 64, I had 49, 25, and 16. Okay, so then to graph this thing, if you look at your instructions, it says to highlight the table including the titles. So I want that. I've highlighted my table, including my titles, and now we want to go to, we want to insert a chart. So we're going to go up here to insert. I'm not going to right click, I want to left click. And we should find a recommended chart. It opens up this, and then we're going to go over to all charts, and we're going to go to XY scatter, which is this guy right down here. And we're going to pick, not that one, we are going to pick this one. I don't want that one. No, I don't want that one. I want this one. Yeah, you can see the difference, what it's graphing here. This one assumes that it's graphing them as independent variables, and we don't want that. This one graphs it as it's clear that this one is period versus length, so this is the one we want. And now we're going to click OK. Boom. And so now we've got our scatter plot. And there should be a plus sign somewhere. Yeah, there's a plus sign. We're going to click on that. We want to make sure that the axes titles, the chart title, the grid lines, and the trend line are all included. And the trend line we want to, yeah, here's what we want. Okay, we'll leave that there for now. Boom. And now we can actually go make some edits. We can edit our axis titles, I guess. So you're going to do this for me, where you actually make one of these using, it's an activity I've got coming up for you. You'll want to change your axis titles to whatever it's supposed to be. So here's this one. This one was, come on. I'm not mouse isn't working. There we go. That's length in centimeters. This one over here is period in seconds. The title of this graph is period versus length for a pendulum. And now we've got this. We've got our graph. We are going to now make some edits to our trend line. Click on the trend line, and then we're going to look at trend line options. Which one is it? Is it that one? Trend line options. Click on the bars, and we can take a look at some different options here to see which line we feel best mimics our data. So it's not going to be exponential. It's not going to be linear. Well, it could be linear, maybe. Let's see if we can find a better one. Logarithmic. Logarithmic looks pretty good. That looks better than linear. It changes it for you as you're looking. Polynomial. Logarithmic. We've got it looks pretty good. Polynomial doesn't look too bad, and you can pick what the order you want it to be. Polynomial of order 2. Or we can go a power graph. Or we can look at what's called a moving average. You don't want to do a moving average. It'll almost never be a moving average. So, where's that last point? That is a point. Okay, cool. So really, there are some times where, unless we're actually using like real regression software, you're not necessarily going to get, the computer's not necessarily going to tell you what your best option is. You just kind of have to go with what you feel looks best. So, you're just playing back and forth between these two, the logarithmic and the polynomial. I think the polynomial does a better job, because the logarithmic, you can see there's a split there, kind of. The polynomial does a better job of actually going through and mimicking all your data. Power is not quite as good, so I'm going to leave it as polynomial. You can change the order if you want. You can do order 3. How does that look? Actually, I like order 2. I'll leave it as order 2. What would order 3 look like? It didn't change my graph at all. Order 3. Can I go half? No. You can change the order of the polynomial till you feel like it gives you a better handle on things. I think that does a pretty good job right there. Now, what we could do is we can scroll down here. One of the bottom options is display the equation on the chart. So you can actually have it on here while you're monkeying around with things. So if I change this thing to power, it's going to change the equation. And you can see here, it's actually going to, it's suggesting that this is 0.2 x to the 0.49. I don't know if you can see that on here, on yours, or what it looks like on yours. But let me see if I can make it bigger. Oh, sorry guys, this is giving me grief. I can't. Maybe if I can zoom in. Why is this not working? I don't have a working mouse, I'm sorry guys. So there I have something that looks like that. As you guys are playing around with it, I won't do that, I want the trend line again. As you guys are playing around with it, I don't necessarily expect you to know what the relationship is. The only reason I'm now leaving polynomial, because if I left it to polynomial, that was the equation. I don't like that equation. That doesn't look, well, I know what the equation is supposed to be. That power equation looks a whole lot better. So it gives us our curved line, and it gives us an equation there, and we can actually take this, we can change it. Y would be the period, and X would be the length, and now we've got a graph. Yeah, We've got a graph now for the relationship of the period of the pendulum and the pendulum, or in the length of the pendulum. I could do the second graph right on here. I could add it right below, and I could say that this is, I would call this, I'm going to go squirt length, SQRT, which is short for square root, and period in seconds. The period data is all the same. I'm just going to copy that down. And the square root of the lengths are 10, 9, which I could get the computer to calculate for me, but it's easy enough to do this, 5 and 4. I'm going to do another one. I'll grab this data. I'm going to go insert. I'm going to go recommended chart. I'm going to go over to all charts. I'm going to go down to XY scatter, and I'm going to pick this one because I want those two variables to be related to each other. This one's not period versus the length anymore. It's period versus the square root of length. I still want to make sure all those other options are there. I want axes titles. I don't need a legend. I want the trend line on there. And you can see this one's a lot more linear. I can click on this now. I can go to my trend line options. It's giving me linear as a default, and I think linear, you could check, but I think linear does a pretty good job of putting all that down. And I can go display equation on the chart, and I'm going to get this equation here. So my line of best fit was had a slope of 0.2. Lots of you guys had a slope with a line of best fit of 0.19. This rounds to 0.19, so your slope, those of you who got 0.19, is actually a better version of the slope of the line of best fit than mine is. This one has a y-intercept that's above 0. But yeah, that's what this looks like in Excel. Comments, questions, concerns about what we've done? Relatively straightforward. Okay, those of you who are working in Sheets, the instructions are similar. We're going to go over here. We're going to go to Sheets. Where is Sheets? It's similar, but it's not exactly the same. I'm going to pull my tables at least over. I don't have to do that again. Boom. So I've got my data. I'll get rid of you. We're going to highlight it. The options are slightly different, but they're similar. We're going to go insert. We're going to go down to chart. I think I said charts in there, but it's just chart. And it goes live immediately, and you can actually change the type of chart over here, and it'll change it for you live. It suggests some good ones. In the chart editor, where's the chart? Go setup. Scatter's the one you want. We've given it the data range. We've told it which one is the x-axis. Like, you can actually do that in Sheets. That doesn't give you options to do that in the same way in Excel. We can add titles. Where do I do that? Use column A as labels, treat labels as text. I don't want to do that. It gives us our title. It gives us our axes labeled right away. Grid lines and ticks. These ones we do need to add. Where are you? I think it's over here to customize. Yeah, here. And go down to grid lines and ticks. Oh, actually everything should have been in customize. Charts and axes, you can give the chart a title, and here's the option for it. You can pick your fonts, you can change the color. The horizontal axis, as we've done already. You can change the minimum and maximum value. We can say, I want my horizontal axis to go from 0 to 100. I want the vertical axis to go from 0 to 2, which it's doing already, so I don't have to change that. I go down to grid lines and ticks. I like to, minor grid lines, major ticks, minor ticks, and we can change the spacing on them as well. I don't want that. If I go step, I want minor spacing. This is the vertical axis. I want the vertical axis to go up by, if I wanted it to do exactly the same, I could put my 0.05 in there, and we have all my little lines the same way I did it on the graph. My majors, I'll leave that alone. If I want to do my horizontal axis, I could change that in here too. I want a minor axis, I want them to go up by, I don't know, 5s. So I've got a graph that's broken like that, and I'm adding in grid lines here. And now to actually throw in the equation. So yeah, there's lots of customization options that Sheets has that Excel doesn't. I prefer working in Sheets. And now we're actually going to through and make an equation. So we're going to go, the Customize menu, which is where we're in, we're going to go over here to Series. I'm going to drop that down. We're going to go down here to Trend Line. And we're going to turn that on. And it's going to give us some trend line options. It's the same set of options: linear, exponential, polynomial, logarithmic, or power series. For the sake of this, I'm going to choose power, because we saw that that was what it was in the other one. But you can do it you can take a look and see, okay, which one you feel best represents this. The thing I like about Sheets better is that it actually extends the data out, out past the data. So you can even say, okay, well, if my pendulum has no length, there should be no period because the pendulum's not there. This line doesn't do that. So that's probably not going to be a great option. Exponential is obviously not going to work. Logarithmic says that a pendulum with some length is going to have no period, which is weird too. So power series is the only one that can slowly start to get us to trending towards that 0.00. Excuse me. So I'm going to throw that on there. Now to actually get the equation under label, where's the label? I've got the series. Where is it? In the trend line options, choose the trend line to fit the data. Under label. Oh yeah, is it data labels? No, I don't want data labels. I want a label, this guy, big, there it is. Use the equation, and it will give us the equation there. This one is 0.201 x to the power of 0.494. And so that's the first data, or first equation, sorry, first chart given the first set of data. I could do the same thing with the second set, just to show you guys what that looked like. Go down over to chart, and now we're going to start to customize this thing. As it puts it there already, because even if you look at setup, you can actually have it switch rows and columns. If you feel like that, oh, no, don't do that. Please don't do that. We don't want to do that. Customize chart style. We can change the colors, the chart and axis. No, I don't want that. We had our scatter plot. Yeah, that's good. And now the last thing, I'm just going to go straight ahead. You can play with the vertical axis. Actually, I do want that. I want the horizontal axes to start at 0. I know I'm almost out of time. Hang with me here. I'm going to add in where is it? Guys, don't pack up yet. Bill hasn't gone. I got 1 more minute. I'm going to add in the trend line. Throwing a linear one does a pretty good job of demonstrating what this thing needs to look like. There's my equation. And so we can use now technology to do some of this stuff for us. And it gives us the equation. It has, how does it compare to the Excel one? The Excel one has, oh, it's exactly the same. So they're using the same recursive algorithms to give us our trend lines. And there it is. That is using, hey, you're packing up so fast. That's using Excel and Sheets to graph this stuff for us. I've got 2 data sets that I want you guys to try to do for homework. Data sample 1 and data sample 2. Sorry, I'll do this, which means I need to bring this back. I want you to try doing what we've just done with these two questions. That is your homework. Bring your computers with you. If you can't bring your computer with you, then save these things and send them to me so we can load them up tomorrow. And we're going to be practicing this a little bit more in depth tomorrow. There it is. Have a great day. Play with those two for homework. If you took a computer from the lab, just leave it up on the table at the front. Have a great day, guys. Please return the rulers and French curves to their appropriate locations.